Hello, good evening. I think two of you have joined. We'll wait for another 2, 3 minutes so that others may also join, and then we'll start the session. Okay, I think we will start our session right now. I'll share the screen and let's begin. Is my screen visible to everybody? If you can give some confirmation, then I'll proceed ahead. Okay, ML says it's visible. Fine, so let's proceed ahead. So, once again, good evening and welcome to today's tutorial session on urban utilities and planning on water supply, sanitation, and drainage. Both of you have been regularly attending the live session, so without much introduction, we'll just proceed further. So, this week, that is week 5, we learned about different distribution system layouts. How do we plan the network? The conveyance of water, like we learned it in two parts. How do we do the calculations and all that? And we also learned about pipes, joints, what kind of meters are used, and what are the systems. And yes, in continuation to our lecture 22 and lecture 25, again, we learned about how do we plan the network, like parallel connection, simple connection, loop connection. So all those we discussed. So we will today try to solve certain assignment questions based on these 5 lectures which we learned. So today's has more of a bit more of theory than numericals. We will do some numericals, but there's some theory questions also, unlike the previous sessions which we had. So let's get started. So this you already know, so I'm not going through that. Just to sum up, you can put it in the chat. You can put your doubts in the chat box, so you can interrupt me anytime. So let's proceed on and move on to our first question. The carrying capacity of a water distribution pipe directly depends on which of the following. So about 4 options are given, and we've been asked to find which is the factor that depends that is which of these factors influence the carrying capacity. So let's go option by option. That is A, which is the size of the pipe. So size of the pipe. So ML says size of the pipe. So ML, does it directly like, so okay, in the option, so this is a box
It
type.
is said carrying capacity, right? Not flow rate.
No, it is carrying capacity, the amount of
Okay.
water that can be it is not the flow rate, it is the carrying capacity that we are
Okay.
discussing.
Then I will size of the pipe.
No, so again, just to tell you that this is a multiple option answer. Like you can have more than one option right. It's not necessary that only one option is right. So let's go. So you're saying size of pipe depends, influences the carrying capacity, directly influences. How can you explain?
Size of the pipe, I am talking about the diameter of the pipe.
Yes, you're talking about
But
the diameter.
but I am not considering considering the thickness of the pipe because the thickness of pipe is a function of the size of the pipe. Means when we design a pipe, we consider the thickness of a pipe as a function of size of the pipe.
Yeah, so
So
here we're mainly talking about the diameter, as you said, the size of the pipe in this, because you see thickness of pipe is there in option D, which means it's been considered as a separate entity. So here, by size of pipe, what the question, what it means is the diameter of the pipe.
okay.
Okay, so so you think that the size of pipe or the diameter of the pipe influences the carrying capacity? Like, does it directly influence?
Yes, size of pipe directly influences the diameter increases. We can have more flow rate through it.
Right, right. So as diameter increases, the flow rate will also increase. So as you say, size of pipe in like the carrying capacity is directly dependent on the size of the pipe. Right. Now, what about velocity of flow? So that probably Devsena, what do
Since
you
you
think?
have already said it is not the flow rate we are considering and it is only the capacity, I would neglect the velocity of the flow. If it is the
Oh,
flow rate, Q is equal to AB, area and velocity will be a direct will be affecting the flow rate. Since we are not considering flow rate, we are considering only the carrying capacity of water distribution pipes.
okay. So here, so if I postulate saying that the velocity is increasing, then the overall carrying capacity in the distribution system, that is the amount of water that can be transmitted to a location, if the velocity of flow increases within that particular time, the amount of flow that can be given, will that not increase?
Again, I am saying the flow rate is increasing. No, I can take a small amount of pipe and increase the velocity as much as the required flow rate I need.
Yes, yes,
It
that is
depends
right.
upon the pressure head that I am keeping.
Yes, that is
But
right.
for a fixed flow rate, for a fixed velocity, I can only vary the size of the pipe to get a maximum flow rate.
Yes. Okay. That point is very valid. That is you're trying to relate the size of pipe and flow rate. That is correct. But the question here asks about what is the carrying capacity of a water distribution system, and all these factors are given. So your logic about how the size of the pipe and flow rate varies, that is right. But when the velocity of flow increases, that is when the velocity of flow increases, the distribution system will also be able to transmit more amount of water. So flow rate, as the velocity of flow increases, this carrying capacity of that distribution system that we design it for, that will also increase, right?
No, my doubt is when you are mentioning carrying capacity, are you talking about the weight or the flow rate? That's
The
what my
volume, the
question.
overall volume that can be given through it. It is not the flow rate, it's
Oh,
not the
then if it
velocity that
is
we are talking
no,
about, but it's the
if we are
volume.
considering the volume, then it will be volume flow rate. No, if the volume flow rate is the answer, then it will be depending upon the size of the pipe and velocity of flow. U is
It
equal
does
to
depend
AB.
upon the value. No, as I said, this is a question which has multiple answers which will
Okay.
be correct. So both size of
But
the pipe also
in the question it
influences.
was mentioned carrying capacity, so I got confused whether it is a weight.
Okay, it
Weight
is
it
not.
can carry. It is
It is
not.
not.
So if it is the volume it is considering, then it will be size of pipe and
Right.
velocity of flow.
Right. Correct. Correct. You're right. So both. So it is size of the pipe as well as velocity of flow, because we are considering the volumetric flow rate, volumetric carrying capacity, which can be done. Right. So what about pipe material? Can Okay. What about pipe material? Do you think that the material of pipe influences the carrying capacity? Again, just to be clear, we are talking about the volumetric carrying capacity, which can be done over here.
Volumetric flow rate. Okay.
Yeah.
No,
Uh,
like I said before, the pipe material and thickness of pipe is always a part of the design. Means
um, okay, pipe. So you're saying pipe material.
in the sense pipe material or thickness of pipe is always designed to the flow rate that I need. If I need a 10 meter cube per hour flow rate, 10 meter cube per hour flow rate, I'll be designing my pipe material to carry that much weight. The pipe material should not have any uh, anomalies during the flow time, and for maximum weight and including the factor of safety also, I'll be designing the pipe material and thickness of pipe, so it shouldn't affect the flow rate of the water.
Right. So here we are again coming back to the question. We are talking about if you have different materials. As you rightly said, we have to choose a material. So based on the flow rate that you need, you're going to choose a material. So now based on different materials that we are going to change, how is the carrying capacity or the volumetric flow rate which is happening in that changing? That is what the question is asking. Even size of pipe, diameter of pipe is also a design factor that you're designing it so that so the first option, as you increase the diameter of the pipe, your carrying capacity increases. So that directly depends. So we said that that is
No,
right.
size of pipe and velocity of flow is not a design, means it is my requirement, right? Demand.
Yeah, so when we have gone through the lectures, you might have noticed that these two, because there's an interdependent relationship which is happening, we either assume initially let the size of pipe be so much
Hmm.
diameter, then we will find what is the velocity that we're getting and whether it's satisfying our design requirement. Or we will see, okay, this is the requirement we have, then what should be the size of pipe that we need to consider. So that relationship we have already learned. But this question simply asks that while designing, that is, when we are designing a pipe, what are the factors that we will consider? That is to look at your carrying capacity, whether we should. So if I want a carrying capacity of 100, so and like I have a fixed carrying capacity that I need. Now suddenly I want to, and I've designed for this. Now I want to increase the carrying capacity like to 200. So what are the things I can change? Like that is what they're talking about, the direct dependency over here. So will I change the diameter? Like will I increasing the size of the pipe, increasing the diameter of pipe? Will it increase? So we have already discussed that it does increase. Now, can I increase the velocity of flow? Can I increase pumping so that I can increase the, like, will I use a high efficient or a high power pump so that I can increase the volumetric flow rate through it? Yes, that also we say that yes, that also increases. Now, can I change the pipe material so that I can have like more volumetric flow happening through that? So that is a question. So what do you think? Can somebody else come up with their observations also, like Supriya, Tamanna, somebody? Do you think pipe material influences the carrying capacity?
Yes, it is.
It is, right. Pipe material influences. So why? Because we have already learned that there is a friction which happens within the pipe, or viscosity we call it. So it usually, like, so if there's a water flowing like this, because of the material, the edges tend to be at a velocity which is a bit lesser than the velocity of the center line. So if we have a material which has a lot of disturbances, or a rough, it's not very smooth, then this friction or the viscosity force which acts will increase further, and it will reduce the volumetric flow which we can go through that entire pipe. So pipe material also influences. What about thickness of pipe? So I think Emil, you briefly discussed about this, about the thickness of pipe. So can somebody else say that what do you think about the thickness of pipe? Would it increase the carrying capacity? Uh,
No, thickness of pipe doesn't
Increase. Okay, why do you
depends on.
feel so?
Yes. Mm, can't say.
Okay, right. So we already discussed that as the diameter increases, the carrying capacity increases. So now in thickness, we're saying we're keeping a fixed diameter, but we're only changing what is there outside. So that does not change anything which is flowing through it. That is still remaining. Thickness, where it comes to play, is that it will be able to withstand external pressure. and as well, so when you have some other external elements coming onto it, if you use a thicker pipe, it is much better. But other than that, the flow rate which is happening through that, it doesn't influence that. So thickness of pipe is not right. So here for this particular question, our A, B, and C are right answers. D is not a right answer. Right? Any doubts in this question? Okay, if not, we'll proceed ahead. Let's go to the next question. So this question asks, match the following and mark the option for the correct match. So they are asking about gravity system, dual system, and pumping system. So basically they're asking about the difference between these. So can one of you attempt this question, like which is the gravity system over here? There are three options given. Any guesses, anything?
C is the option, correct option.
C, you're saying C is the correct option. Anybody, any difference of
Yes.
opinion? Okay, you're saying C is the correct option. Like, oh, okay. You went directly to the option itself. Wow, nice. Um, okay, that is good. Uh, okay, so let's see whether okay then Supriya, you can you please explain why you feel C is the right answer?
See, the gravity system is always follows the contours, or you can say the slope where naturally slopes is going on. So the third is reservoir is at higher level and it's going down to the town area. So
Okay,
it is a gravity, and the pumping system, pump house we can see, and the reservoir is at lower level. So intake point and then pump house is pumping the water to the town area. And for
right.
dual system, it is like water is being pumped to the elevated reservoir. From there, the water is distributed to the town. So it is a dual system, pumping plus the storage reservoir is there, and then it is
Very good.
distributed to the towns.
Very good, very good. So that suffices everything. Yeah, that's the right explanation. So basically, in gravity system, it is only gravity which is happening. No mechanical or no pump is involved. And when it comes to your pumping system, there is only a pump which is involved, and there is no, you're not using gravity at all. You're fully pumping the whole thing. And when it comes to the dual system, you have a pump plus you're having the gravity, and that you can see over here. You have a pump house plus you have an elevated reservoir. So using this both, water is being given to the nearby town. So very good, that is the correct answer. Any doubts in this particular question? Anybody else? ML, any doubts?
No doubts.
Okay, cool. Let's proceed further. So identify the water distribution layout for the given distribution layout, like which one this is. So you have option ring system, interlace system, dead end system, and radial system. So let's look at each one, what we've already seen them in the lectures. So sorry, I went to a different question. Yeah. So let's go from behind. A radial system. How does a radial system look like? So radial system basically, it has certain main points and there are certain intersections, like so you keep your like the main storage, the pumping happens from here, and you rate you, so this will be your main point from where all these are interlinked. There is a loop, and from here you keep pumping to all the nearby, so you follow a grid. Again, these are also interlinked, so from here it goes here. So basically there is a center portion from where, and there are certain multiple distribution places, and from there you start giving it out. So that is your radial system. And then so that then you have a dead end system or a tree system. That is this is also known as a tree system, where you have mains and then you have something branching out of it. So this is also a branching system. So you have a main and then you have different branching systems coming out of that. Then the next option talks about an interlaced form. So what is an interlaced form? Or this is also known as an iron grid form. So where you have, it's completely rectilinear, like you have a completely laced form and you have a mains which is running over here. So this will be the main. And from the main, you have all these different arteries coming out, but it is in a proper grid manner, which will be going. So it is again a complete looped system which is happening. And then we have the ring system. In ring system, in interlaced form, you have the center, one is the mains. In the ring system, you have the borders as the main. So you have something, and through the border, all the main, this will be the main pipe, and then there are these interlinkages which are there. Oh, sorry, which will take the water from the main to the residences which are there inside. So now let's see which is the system. So anybody, which is the system which is shown in this particular figure?
It's B, interlaced system.
It is, you think it's an interlaced system?
Yes.
Okay. Anybody else? Do they feel anything else?
No, it can be ring also.
It is a ring system.
Okay, so we have two answers, ring system. Can we have some response from Tamanna and Devasena? I think they've been a bit silent because we're having a confusion here. One person says interlaced, one person says ring. So what do you guys feel? No response? Chat box? Okay, Devasena says it is A. So let's go by the majority. Let's go by the voting system. Will that work?
Yes,
Majority means
Okay.
ma'am.
Yeah, Tamanna, sorry, I couldn't hear you. Okay. I think I can't hear you. Right. So, I mean, not going by the majority, but the answer is ring system because, Supriya, the thing is here, there is no, there is no central main which is there. So, in the rectilinear or interlinked system, you have a central main, and from that, you everything is diverging, and then it comes back in a loop. But if you observe, here it's clearly shown that it is directly going outside. So the mains which is happening, I mean, you need to see that like the mains which, because this is a bigger arrow which shows that it's not small arrows going like this. It's the big arrow which shows that this is the main which is happening. And then from here it is branching out. These are the small branches which are coming out. So it is actually a ring system over here. The boundaries have got the mains, and then whatever residences or whatever is there inside gets through these arteries. I hope that's clear.
Thanks.
Let's go to the next question. Now, which of the which statement among the given statements is incorrect? So you have four options for this. Let's go by first each option and say whether this is correct or not. So helium is used to detect water leakage in a distribution system. Is what do you think? It's right or wrong?
it is
It's
wrong.
right.
Supriya says it's right. ML says it's wrong. So let's start with ML. Why do you think it's wrong?
Because in very economic way, helium is a kind of very costly and one more thing is there. Okay, to detect leakage, helium is a very uh, in the periodic table, it is the one with the smaller molecular size, so it will leak through any pipes. So to contain helium, we need specially made valves, specially made containers. So
Emil, don't
I
you
don't
think
know.
the answer is there in what you just said?
Means it detects the pores. But if
Exactly.
you are the thing is, like I am saying, the economic factor.
Okay, probably the
Economic factor I am
question,
thinking.
see, okay, you're talking about an economic
Because
factor and
helium will pass through. If I keep a glass jar, helium will pass through it. But if I am using that for a water leakage test, water may not pass through it.
see, okay, you're looking at the chemical properties and then you're talking about, but the question is simple and it just asks us whether it can be used to detect water leakage. So yes, economically, probably what you're saying might be right that it might not be a feasible, so it might not be the best solution. But industry, it is used to detect water leakage. The tracer gas experiments are very common in finding leakages in any system like water leakage, air leakage, everything. Use of helium is a very common practice which is used. Maybe economically it's not feasible, maybe we can come up with something else, but this is a very common practice which is there.
No, I was saying economic factor because helium is mainly helium is not easily available. It is a very rarely available. We obtain it from the petroleum rigs and everything. And I work with helium, so I know.
Okay,
You
okay,
can say.
okay. That's interesting to know. Could you tell a bit about yourself? Like, what are you doing?
I'm a cryogenic engineer.
Right, right.
Uh, I'm a cryogenic engineer. I work on carbon capture, but in that also I have worked with helium. In that experience only, I know that for helium, we cannot use a CO2 cylinder to contain helium because it will leak out. We cannot store helium in any other cylinders other than specially made helium cylinders because of the helium's very small molecular size. With every normal containers, it will leak out through the pores, like what we have seen in the Kujas. Transpirative cooling, transpirative cooling of Kujas. The water, how the water comes out through the Kuja and cool itself.
Evapotranspiration is what you're saying, right?
Yes, evapotranspirative cooling.
Right,
Likewise, helium will act like that in
right.
normal containers.
Okay, thanks for sharing that information with us. I am not what metal expert. Like, I don't know about all these
It's
much, but
okay.
then
No, no, no. I
I
was
know that.
sharing my
But then the fact is that it is commonly used
yeah, yeah.
in this one. That is not just in water supply pipe leakages, water supply leakages. It's also used for air conditioning systems to find leakages in ducts and all that. So it's commonly used. It is used as the element in order to detect leakages in any distribution system.
Yeah,
Right.
I don't have much industry experience maybe because of that I don't know. It's just I am just interested.
Okay,
That's the
cool. So
second.
let's look at the next option. Uh, Option B, water pipes laid in parallel induces same head loss in each pipe. What do you think about this?
It's true.
It is true. So, Supriya, what varies? If head loss is the same, what is the one that is varying?
Sorry.
You're saying that when water pipes are laid in parallel, the head loss is the same
Yes.
in each. So,
Yes.
if head loss is the same, what is changing? Like there should be some change, right? What is changing?
Mm,
Okay, so let's see if we have a loop like this, and if it's going in parallel, let's say it's going in parallel, and then it comes. So what we're saying is the head loss which happens over here, that will be the same. But at the same time, when the head loss is changing, the discharge, whatever is happening, so discharge, whatever was here, will not be the same over here. The discharge basically, so it is a discharge which gets split into these two pipes and then goes, and when it comes back again, it joins. So it's similar to our resistance, parallel, and series connection. So when it is in series, Supriya, what happens? If you have A, B, C, would the head loss change or will it remain constant?
will remain constant.
Yeah. So it will remain constant when it's series. So from A to B, I've got head loss HL1 and HL2
No,
and
those will be
HL3.
different.
No, no,
It
no, no.
depends
Sorry.
upon the length. A to
It will
B,
change.
A to B. If
Yes.
the length are the
A
same,
to B and B to C and C to D. We can.
hmm.
Yes. Yes.
And just to, I didn't get the point that you said first. So
Yes.
what
You
about
can
the
continue.
discharge in that parallel connection? What about the discharge?
The discharge will get split. It will change. So then it depends on the pipe properties also. Like,
No, even after, okay, just imagine there is a discharge of 10 meter cube per 10 meter cube in the entry, and after it is split up into 4 or 6, and
hmm,
after the head loss, it is
hmm,
reduced,
hmm.
and coming to the next point, it will be always summative, right?
Yeah, it will
Summa-
be. Basically, yeah, it will be. It will be. So there'll be some loss also which is happening in between. So if you remember in our in the last one where we're designing the network system, we've looked into this, that how it splits and
Okay, so
how we
you are
have to.
saying the discharge at before the join and before the split and after the joining, those are different. That's what you are saying.
Yes, yes, it
Oh,
can
okay,
vary. It
okay,
can vary. Yeah.
okay.
Yeah, right. Okay. So this option is also right. That is, the first two options are right. Now the second one, velocity of water in a pipe is inversely proportional to the hydraulic radius of the pipe. So what do you think about this one? Is it inversely proportional to the hydraulic radius?
Mm,
first let's
Yes,
dis
it is. It is
it
right.
is
Inversely proportional.
it
Q
is
is equal.
inversely proportional. Okay, both
Q
of
is
you are
equal to
saying it's
AV.
inversely proportional.
It is right.
Okay, let us discuss what do we mean by hydraulic radius. Is it the normal radius of the pipe that we are talking about?
It is the wetted wetted perimeter by area something.
Yes, yes, you're right. You're right. Hydraulic radius, or you also know call it the hydraulic mean, which is give me a second. Yeah, hydraulic radius or hydraulic mean is basically the it's usually the area of the pipe
By
divided
the
by the
wetted
perimeter
perimeter.
of the pipe. So for a circular pipe, we can take
It
it
is the
like,
radius.
yeah, it is easy. But now, in this question, you've been asked to find the relationship between the velocity of water in the pipe and the
Yes.
hydraulic radius of the pipe. So, if you recollect, we learned about Manning's formula in order to find in order to design the velocity, like how do we plan it. So, that formula, so I'm just writing Manning's formula, which is 1 by V is, V is equal to 1 by N into R raised to 2 by 3 into S raised to 1 by 2. This is the formula. So where v is the velocity and n is our Manning's roughness coefficient.
Mm.
And yeah, one sec. Yeah, Manning's roughness coefficient, and r is our hydraulic radius that we are talking about.
Okay, so it is directly related.
Yeah, and what is s? S is your hydraulic gradient or the slope of hydraulic gradient. S is your slope of hydraulic gradient. Basically, it's HL by H. We will discuss that in the coming problems. So this is the formula. So yes, so based on this, I mean, you can't say directly related, but V is directly proportional to R raised to 2 by 3. This is the proportionality which is there. So
But
this,
can I ask one doubt?
hmm,
In Bernoulli's equation, we learned Q is equal to AV.
yeah.
So, as the area to keep the flow rate constant, as the area changes, the velocity has to decrease, or as the
Yeah, but
velocity.
you're right, you're right. But I think you're getting confused with the this one. Sorry, I'm just going to a different page. Yeah, you're getting confused with the normal radius and the hydraulic
No,
radius. So we are,
hydraulic radius, okay.
huh.
But what is the variation of hydraulic radius with respect to the area of the pipe?
See, yeah, with respect to area of the pipe, it's directly proportional over here.
If it is directly proportional, then velocity should be inversely proportional to the hydraulic radius, right?
One sec. What you're saying is that you're talking about equation like A1 V1 is equal to A2 V2. So you're saying
No,
that if,
no, 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 no. Okay, okay.
yeah,
Tell
so
me.
So
equation
Q
of
equal.
yeah, so this is your logic that you're saying, right? Yeah, I mean,
This is continuity equation.
yeah, continuity equation. So as per continuity equation, you're saying that velocity and area are inversely proportional, right?
Mm.
Yes, actually, I was also considering the same.
Yeah, so if velocity, so as area increases, velocity will decrease, right?
Mm.
And area, okay. So again,
Mean.
in
uh,
area also you have like let's take a circular pipe. So, I'm just keeping on going to a different slide. Then if that's the case, your area is pi r square divided by your perimeter will be 2 pi r. So here again your let's yeah. So the problem here what happens is that in area also you've got this radius factor or basically the size or the dimension of the pipe which is coming. In your perimeter also the dimension is coming. So whatever this direct relationship that you're talking about in terms of area and velocity will not hold for your hydraulic radius case because hydraulic radius also involves the same parameter that you're using in area. So that relationship also comes into play. Getting me?
I am not getting you.
Okay. What I'm saying is that as area increases, your perimeter will also increase. Like, can that is also true?
Okay.
So there is a relationship which happens between
Okay.
that. So when you're talking about velocity and area, so okay, your velocity increases, velocity and area relationship we have established. But here we are talking about hydraulic radius, which means it is not just about area. Like we cannot draw a relationship by saying that because since area increases, since area and velocity have a definite relationship, the same relationship will happen for hydraulic radius also, because in hydraulic radius you have one more parameter. You have the perimeter parameter also, which is there, and that perimeter is also perimeter and area also have a relationship which is happening. So here what we need to consider, so that is otherwise to design our velocity of pipes itself, we could have used the continuity equation. So we have, in the lecture we have discussed that this is also, Manning's formula is also derived from our Bernoulli's equation, which has this, like Bernoulli's equation is eventually again related to equation of continuity, right?
No, is
So
the derivation for Manning formula is given in the lecture?
yes, it is there. No, the overall derivation is not there, but we are discussing about Bernoulli's equation, and from Bernoulli's equation we are discussing that we'll do some rearrangement, and that is how this formula is being arrived. If you
Okay.
notice in the lecture, in our lecture, I will give you which lecture, which this one it is. You can probably refer that and then see in detail. Just one second. Yeah. So it is in lecture. Okay. How do I share this now? I think I will share this screen. One sec. I'll just stop sharing this particular screen and I'll share the other screen so that.
Okay.
Yeah. Yeah. So I'm just sharing the screen from the lecture. Okay, is it visible?
It is visible.
Yeah. So this is from the Bernoulli's equation. We found what is the pressure head, velocity head, elevation head, and all that. And from here only we are coming back. We looked into Darcy-Weismann's, and then finally we are coming to Manning's formula. So here, when we are discussing in the lecture, if you observe, Professor talks about how we rearrange all these, and based on that is where we are deriving all these equations. So there is some relationship which is there. The detailed relationship, if you want to know, I think you can look that up yourself. Like within this scope, it might be a bit difficult to go into the detailed derivation, but it is related. So here, what we are supposed to be using is a Manning's formula, because that is what we have learned in order to find the velocity in pipes. Using direct Bernoulli's equation is not feasible, and that's the reason why we have derived based on that. So let's go back to our lecture now. Sorry, let's go back to our questions now. So yeah, I understand the confusion which was there because you're trying to reason it out using a different method. But here, just
No,
keep
but
in mind
I
that
am still not getting why Bernoulli's equation is not feasible there.
okay.
No, maybe my thing. Okay, let me just look into lecture
No,
once
I'm not saying
again.
it is not
One
feasible. The thing
reason
is, it is
is
simplified. Yeah.
yeah,
Supriya is saying
I
something.
recall, yeah, I recall something from the lecture. It was like if a circular pipe is there, water is not filled to the whole perimeter. So if water is half filled, then we take the
Hmm.
hydraulic radius as diameter by 4. If I remember
Yeah,
it,
that is
it was
means yes,
yeah.
Supriya is right. Means it is not area by perimeter; it is area by wetted perimeter.
Yeah, it is area by wetted perimeter. Yes, yes, you're right. It is
So I
wetted.
think that is the reason only we have this different hydraulic radius. Water flow जितने area में हो रहा है, we take the radius of that only. That is applicable for circular. For rectangular and all, it will
It will
be
vary, right?
Okay.
Exactly. Yeah, Supriya is absolutely right. That is it. So yes, so we are talking about area, wetted area by wetted perimeter. So your relationship using this area and equation of continuity doesn't apply over here, right? Cool. So this one is wrong. Now let's look at the next one. Hazen-Williams formula incorporates the frictional properties of pipe material. Is this right? Okay, let's see what Hazen-Williams formula is. So
yes, it is right. The option is right.
yes, D option is right. So in Hazen-Williams formula, when we discussed itself, we discussed about how it takes into friction. So Supriya, where are we taking friction into consideration over here? In the formula, I'm not seeing anything.
Friction is taken in S. S is slope of the hydraulic grade line, right? So I cannot tell you point to
S is
point,
equal
but
to HL by L.
HL by L. This is the head loss, I guess, the
So
formula
you're saying
HL
in
by.
head loss it is being taken into consideration.
Yes.
Okay. Okay. But also there is this constant that we have. Is it there in this
Coefficient.
one? The numerical constant which is there. So yeah, so here also in this numerical constant also, this 0.85 is derived for a particular friction value, that is for a friction slope of 1 by 1000. When that, so yeah, as Supriya said, this is exactly where we have that in our main equation where we come. But then based on this, like if the friction slope varies a lot, if we don't vary this numerical constant, we can even get up to like plus or minus 30% to up to 50% error can also happen in our the design. So this also we discuss. So because of that, this formula cannot be used in all applications. For this particular slope of 1 by 1000 only, we can use this because this numerical constant has also been derived based on the slope, right? So yeah, so we are coming back to the question. So our option is option C, where velocity is inversely proportional to the hydraulic, hydraulic radius of the pipe. So this is the answer. Fine. So let's proceed ahead. So now we'll have one numerical. These two questions will be based on this numerical. It's a very simple numerical. So for a city with a population of 10 lakhs and a water consumption rate of 200 liters per capita per day, water needs to be supplied. Flow velocity of water in pipes is 1.6 meter per second. Coefficient of hydraulic capacity is 130 and the maximum daily demand is 1.8 times the average daily demand. So question 4 asks us to find the diameter of supply pipes leading to adequate service reservoirs. So what is the diameter that we need to use? So any idea which formula we will be using over here? Okay, this is a very simple application. We need not go into complicated formulas. Let's just take the normal flow velocity is equal to quantity by area. We just need this. Well, the normal like velocity is equal to quantity by area. So in this, what is the information that we have? Like, so we have the population, we have LPCD. So can we find, and we also have the maximum, like the peak demand, how much will it be? So can we not find Q from this? That is Q will be equal to like Q max, like for the peak demand, it will be equal to 200 liters per day into our 1.8 times they've asked to find. So 1.8 times that. So how much does this work up to? Into 1.8? 360 LPCD for like this is the peak demand which is there. So now Q for the total number of population would be, we need to multiply it with 10 lakhs. So it will be again 360 into 10 raised to 6 liters per day, like per capita is not there, liters per day. So in Q, if to use in this formula, we need to make, so this is, we need to make it into meter cube per second. So can you quickly do that conversion to make it a meter cube per second and tell me what the answer is?
Point 166.
0.1, yeah.
4.166.
Yeah, 4.1666, yeah. So 4.17 I can write it as, right? Cool. So so we got Q. So now what we have been asked to find is the diameter. So area we'll write it as pi by 4 d square so that we can get d. And v, the velocity is also given 1.6 meter per second. So let's just substitute the values. So substituting, we'll be getting 1.6 is equal to our q 4.17 divided by pi by 4 d square. Yeah, so now I think this can be solved very easily. Yes? Yeah, 1.82 is the answer. Any any doubts in this particular question for anybody? Okay. Supriya, shall we proceed further?
Yes, yes.
Okay. So, yeah, so I just put it here. Yeah, so now the second, okay, the second part of this question is that for a city with a population of, yeah, so this initial part is the same. Now, determine the hydraulic gradient of the pipe using Hazen-Williams formula. So we have already discussed Hazen-Williams formula, what it is. So I'm just, have I left a space? Yeah, yeah. So I'm just rewriting the formula where V is equal to 0.85 into CH into R raised to 0.63 into S raised to 0.54. Now, what all do we have? So we know V is equal to 1.6 meter per second. This we know. CH, yeah, what is CH? So here, going back to the question, the coefficient of hydraulic capacity is 130. This is what CH is, the coefficient of hydraulic capacity. So CH is given as 130. And now, what is the next one? R. So R we discussed, it is the hydraulic radius that we are talking about. So that is equal to area, wetted area by wetted perimeter. Sorry, yeah. Last time, because I forgot to mention that, it created some confusion. Yeah. So it is the wetted area by wetted perimeter. So here we are assuming that it is fully flowing, like the pipe is fully flowing. It's not partially flowing. So the overall area by perimeter we will take. So we will get it as d by 4. Like if I'm taking pi by 4 d square divided by, okay, yeah. So from this, we will be getting it as d by 4 will be the hydraulic radius. Fine. And what else do we, yeah. So now S is what we have been asked to find, sorry, the hydraulic gradient line. So this is the hydraulic gradient line which we need. So I think now we can just apply it over here. 1.6 is equal to 0.85 into 130 into now, yeah, so okay, so D we already, what is D? We already found it in our previous question. So we are just using that 1.82. So it'll be 1.82 divided by 4. Uh, so I'm just, yeah, this one, the whole raised to 0.63 into S raised to 0.54. Yeah, can you quickly solve this and find what S is? First we can find
Can you
what is
show
S
me the
raised to
answer?
0.54. Huh?
Can you show me the answer?
Sorry, you're not very audible. You're very,
Can you
it's,
just show me the answer option?
yeah.
A, option A.
Okay, you're saying it's option A. Let's just see. Can you give us these answers? What is S raised to 0.54?
Hydraulic gradient of pipe.
Sorry, I can't hear you.
Okay.
Yeah.
I have done all of them together.
Okay, then tell what is S. What is the, okay, you got it
Yes,
as
I got it as 9.18 10 raised to minus 4.
9.86 into 10 raised to minus 4. No,
9.83 10 raised to minus 4.
this one, like what I've written.
Yes.
And you're saying it is option A.
This asked in percentage, right?
Yeah.
X gradient.
If it is
Uh,
asked in percentage, then which is the answer?
okay. No. Because, okay, 9.8 D is.
D.
Wait. What is the unit of S which is for Hazen-Williams formula?
It's a gradient line, no?
Out to be 0.
It's it.
Wait a second. It will be 0.0098. It is A option.
See, the options are asking you in terms of percentage, right?
Yes, that's why I'm telling you A will be the answer because it is coming out to be 0.0098. If you decrease 2 zeros for percentage, it will be 0.098. Oh, sorry,
Okay.
it is B.
Exactly. It is B. It is
0.0.
0.098. Okay. Yeah, so I'm just filling these answers like this one you will be getting it 0.0237, something like that. And yeah, and as Supriya said, it will come as this one. So we will put it as option B is the answer. Right. Let's proceed further. Data required for water distribution network design include population, like which of the following? So let's go. Does population is population characteristics important?
Yes.
Yes. Why it's important? Because as the population if population increases, then the demand also increases. If the population
Yeah, because
characteristics, yeah, their lifestyle also influences the demand. So because of this, we in order to design the water distribution system, that is important. So A is important. Water demand,
Yes.
yes, water demand, because obviously we need more. Topography. Now, how does topography, do we need topography data?
Yes.
yes.
Those elevation, friction loss, and
Very
everything
good.
depend
Yeah,
upon
we
the
need
population.
topography data. Land use characteristics,
Yes, obviously.
obviously. So yeah, this is a very simple question. All of them are required. Let's proceed further. Now, in complex loop network for water distribution, which of the methods can we use? Is equivalent pipe method, can that be used over here? So we are talking about complex loop network over here.
No, equivalent is not B and C. B, C, D is the correct answer.
BCD is the correct answer. That's what you say. Okay. So, Supriya, why not equivalent pipe method? Why cannot we not use it?
I don't have the answer.
Yeah. So basically, equivalent. So we learned about simple loops and complex loops. So simple loop is something that it comes, it loops out to something, like it loops, like probably it just goes this way, and then this way. There are not much complication. There is only one loop which is there. So when there is one loop, we can convert this entire loop to an equivalent pipe. That is what the equivalent pipe method does. Like we will consider the water flowing through this entire loop to be flowing through a linear equivalent pipe. But in complex loop, what happens is that you have multiple, like for instance, you have water coming in over here, it goes, there is one loop which is happening here, there might be another loop which is happening here. So there's one loop here, there's one loop here, there's one loop here. So when there are multiple loops which are like intersecting, then you cannot use an equivalent pipe, like you cannot reduce this to an equivalent pipe, it becomes very complex. So for this, we need other methods. The normal equivalent pipe method is used only for a simple loop, and for complex loop, we cannot use it. So we use other methods such as Newton-Raphson linear theory. In our lecture, we mainly learned about the Hardy-Cross method. This we did not discuss in detail, but Hardy-Cross method we discussed in detail, where we assume one value, and then we keep iterating and improve that value until variations are like much our error is reduced. So yeah, so you're right, option B, C, and D are the answer. In complex loop we need to use more complicated methods. Let's proceed further. In Shezzy's formula for open channel flow does not consider which of the following? So let's write the formula first so that it becomes easier. So what is Chessy's formula? Q is equal to A into C root M into I. Now what is A? A is the area of flow. Area of flow. And what is C? C is this Chessy's coefficient, it's called, yeah. Chessy's constant, it's called, yeah. Chessy's constant. And M is our hydraulic radius or hydraulic mean, it's called. So that's the reason why it's M over here, hydraulic mean, and I is basically our slope. So now let's see. The hydraulic mean depth is also considered. Yes, so this is right. Slope of the pipe, is it there? Slope of the pipe, it's there. Yeah, I is there.
It,
Yeah, I
yes.
is there. Slope of the pipe. Length of the pipe, is it
It
there?
is not.
It
It
is
is not.
not there. And area of flow is obviously there. So it is length of, this is the right answer for this. Length of pipe is not considered in Chessy's formula for open channel flow. Okay, next question. Dash are used to determine the volumetric flow of water directly from its velocity. So, all these are used to infer volumetric flow, but directly from velocity, which of these uses? Any guesses, anybody?
Rotary piston meters?
Tamanna says it's electromagnetic meters.
No, I am saying rotary
Yeah, I
piston
heard
meters.
Emil says it's rotary piston meter. Okay, anybody else? Any other observations? What do you feel? Supriya, any guesses?
Electromagnetic meters.
Supriya also says it's electromagnetic meters. Asmita, any guesses? Okay, so we are like 2-2 now. This has become difficult. So I think Devsena, you have to resolve the conflict. What do you think?
You can vote for Devasena.
No, if she let her. Hello, Devsena, are you there? Okay, so I'm not voting. It's 2-2. Let's see which one it is. So this is what we discussed in our one sec. Site is, yeah. This is what we discussed. So we have volumetric meters, and rotary piston meter is a type of volumetric meter which can directly measure the volume of flow. So in this, there is based on the display, like it's a displacement meter that is based on how much of water the volumetric flow is happening. We can directly measure that. And when it comes to our electromagnetic meter, there is a conversion which is required. So there is a magnetic field which is created, and because of the movement of this water, there is that it induces a difference in voltage, and because of that we get it. So it doesn't directly measure the volumetric flow. It is a rotary piston meter which can directly give us the volumetric flow. Then we have also discussed about inferential meters and ultrasonic water meters. Again, these are again inferred. So you see, we infer it from other different factors. So over here, the rotary piston meter is the right answer. Right. So let's proceed further. Um, yeah. So the pipe material that are commonly used now in water distribution lines are glass reinforced plastic, polyvinyl chloride, high density polyethylene, or asbestos cement. Which is it?
B, PVC.
BCD.
Yeah, this is a question with
Oh,
multiple
multi
answers,
choice.
right? Yeah,
Okay.
multiple answers, right?
Commonly used in water. Okay. PVC, HDPE. I don't know about B
Okay,
and A.
so glass
Yes,
reinforced
cement
plastic.
is also used. Cement asbestos.
Yeah, okay.
For bigger pipe, yes.
Okay,
B,
so
C, D.
let's discuss one by one. So you're saying glass reinforced pipe is used? Yes.
Uh,
No,
okay.
no.
Glass reinforced plastic is used. We've discussed that in our lecture. Like all glass reinforced plastic, PVC, polyvinyl plastic, high density polyethylene, all these are used. This is commonly used nowadays. So, and also the question they are discussing that nowadays, which is commonly used. So, all these three are used. Like in plastics, are new mostly now commonly plastics are being used more frequently than before. So, this is used. And as Supriya said, cement is used. Yes, you're right. PCC and RCC pipes are there, but here you're talking about asbestos cement. So let's look at why this is not used. So you're right. Initially, it used to be used, like in the early times, asbestos cement was used, but nowadays, or until the health hazards of that was found, it is not. It has been it's been taken off, withdrawn. Like now, it's not common because mainly it causes a lot of lung cancer and other diseases because it has these asbestos fibers in it. So because of these health hazards, asbestos cement is not commonly used now. So yeah, so the answer is A, B, and C, and D is not used. So I think the what we have to learn from this is that when we know that cement is used, we also need to see what type of cement is also used. This asbestos cement, AC cement, making pipes out of it is not used these days. Okay, let's proceed on to the next question. Dash has a least coefficient of thermal expansion. So this is a very, very simple question. I think you can get that.
Concrete pipes.
Yeah, concrete pipes. So it's compared to all the other pipes, concrete pipes has a least coefficient of thermal expansion. We've also learned that in when we use UPVC pipes, we cannot even put hot water in it. Like it's used for cold water movement. Like that also we have learned. So yeah, so this is a very easy question. I'm just proceeding further. So yeah, so I mean, this was just to now with time. I have one more question, so I'll just go to that question itself. Yeah, match the following and mark which is correct. So you're, I hope it's visible. So you're talking about screw joint, flange joint, and socket joint. So which is which?
P is 2
P is
and Q is 2, Q is 4 and R is 1.
So means P is 3, P is 2, and R is 1.
R is one. Okay, R
Means
is one.
P is 2, flash joint is 3, R is 1, digit and socket joint is 1.
Uh, okay, so here screw and flanged. I think was there a I think there was a difference in opinion, right? So
Yeah.
once more, P is one. P is two or three.
P is 3 according to me.
So ML says
2,
P.
2. It's 2.
No,
No,
sorry,
no,
sorry.
P is 2.
P is 2, flash joint is 3.
You're saying screw joint is this one.
Yeah, that is screw joint.
Yes.
No, okay. Okay, that is screw joint, and your flanked joint is this one, right?
Third one.
Yeah,
Yeah.
right. Right. So this we have learned. So this is our yeah, absolutely right. Flanked joint. So I'll just mark it here. So this is flanked joint and this is screw joint. Right. So there's no confusion in this question, right?
No.
No. Okay. So I think that's all I wanted to discuss with you today. If you have any other doubts apart from whatever we discussed, you can, or in this also, you can ask now. Yeah. So, previous class you had asked about some assignment questions being incorrect and all, right? So I think that has been resolved now. Like they have identified that there was a mistake in the option, so that has been resolved. I hope this assignment there won't be any
Yes,
mistakes.
that was question number 8.
Yeah, I remember you asking.
No, I
So
couldn't find it.
yeah, don't worry. So when such mistakes happen, you'll get grace marks for that. So that I mean, it was a mistake from the NPTEL team, so that'll be sorted. So now this assignment also, if like the other one, when you're doing, if you have any difficulties, put it in the
Will we be
discussion
getting
forum.
grace marks? It only the questions, the announcement was the question gets cancelled, right?
Yeah, yeah, the question gets cancelled, and yeah, the question
We
gets
won't get
cancelled.
any grace marks, I think.
Okay, okay. I'm not aware of that. That's done by a different team. So I was informed that we need not worry about it. That question's
No,
being taken out.
this was the announcement shown in this one, the
Okay.
portal.
Okay, okay, fine. Very good. So I hope we can conclude with today's session then. So see you all next week. Have a nice evening. Bye bye.
Yeah.
Yeah.
Thank you.